Good evening, everyone. Welcome to this interactive session on aircraft design, and this is week 7. So, in this week, professor has discussed about mainly this week was about wing loading. So, he has discussed wing loading for maneuver, climb, and glide. So, as I discussed in the previous class that we have to estimate the thrust loading and the wing loading for different phases of flight. Okay, and after doing that, then we have to compare and see that which phase of flight we have to give priority to. Like, so if you consider a normal aircraft, if you consider an aircraft with a normal mission like this, okay, with a takeoff and then climb and cruise, loiter and landing. So wait a minute. Takeoff, climb, cruise, loiter, and landing. So for each of these phases of flight, we have to use the fundamental equations to find thrust loading and wing loading. Then we have to see that which phase we have to give priority to, and according to that, we have to select values for this. Okay. So So this week was about wing loading. So first he discussed wing loading for maneuvers, climbs and gliding. Then he discussed wing loading and thrust loading for takeoff. So we have discussed this in the previous week also, but this time it was done in more detail. Then he discussed about high lift devices. So high lift devices are flaps and slats. Flaps and slats. So he has discussed that why these things are necessary and how like in which phases of flight they are used. And then here he has discussed wing loading for approach and landing. So what is the wing loading for approach and landing phase? So I will briefly go through, like I will briefly revise previous week's topic. So in previous week we learnt about thrust loading, power loading, and wing loading. So thrust loading is the thrust by weight. So thrust by weight, this quantity is called thrust loading. It shows you that how much thrust can the aircraft produce as a fraction of its weight. So obviously a higher T by W means a more powerful engine and a more powerful aircraft. Then you have power loading, which is similar to thrust loading, but it is meaning wise it is opposite. It is weight by horsepower. Then you have wing loading. Wing loading is weight by the wing surface area. So it basically indicates that how big of your wings are, because the wing loading ratio tells you that how much the the wing loading ratio tells you that the weight is distributed over how much surface area, and usually the aircraft weight is fixed during the design phase, so mainly the surface area changes. So if your wing loading is low, this means the surface area is larger, and if wing loading is high, it means that the surface area is lower. So note that power loading is inversely defined compared to thrust loading. So inversely defined means, like, what I mean is that meaning wise it is inverse, because you can see thrust loading is T by W, whereas power loading is W by HP. Then again you can derive the equivalent thrust loading for a propeller aircraft. Uh, So propeller aircraft, we mainly talk about power loading, okay, or we may talk about HP by W, horsepower by weight. So we can find the equivalent thrust by weight also using this formula, where V is the velocity, and uh, eta is the propeller efficiency. Okay, so these are some common thrust to weight ratios and horsepower to weight ratios for different types of aircrafts. So these are so all these tables have been taken from Raymer's book, yeah, Raymer's aircraft design book. So now we'll come to the uh, first first topic, which is wing loading for maneuvers. We'll come to the first topic, which is wing loading for maneuvers, and here we'll discuss about instantaneous turn rate. So usually when we talk about maneuvers, we talk about some kind of turning. Okay, we talk about turns, and turns can be classified into two types. So turns can be classified into two types. One is instantaneous, and the other one is sustained. And what is the difference between these two? So, instantaneous turn rate. So, first I'll talk about the sustained turn rate. So, a sustained turn rate means that the when the air see if when the aircraft is cruising and we look at its front view. Suppose this is the front view. Okay, so we know that the lift acts up and the weight acts down. So these forces they cancel each other and hence the aircraft stays in equilibrium. Now when we are turning, the aircraft has to bank by about 20 to 30 degrees, and so in that case you will see that the lift acts offset from the vertical. So here the lift is acting towards the side, whereas the weight still acts downward. Okay, so the weight acts downward. So there is a theta, bank angle theta. So you see here that the lift is offset from the vertical. So it means that uh, the aircraft may the lift is no longer cancelling the weight. Okay. So during a turn, if things are not properly balanced, then the aircraft may start to fall. Okay, it may start to lose altitude and lose velocity. So in a sustained turn rate, the thrust is increased and the angle of attack is also increased so that the lift is increased. Okay, so the lift becomes a multiple of the weight. So in cruise condition, we know that lift is equal to weight, whereas in a sustained turn condition, lift is equal to NW. It is more than the weight. Why? Because see, component of the lift will act to cancel the weight, whereas the rest of the lift component it will make the aircraft turn. So So in a sustained turn rate, lift is equal to Nw and thrust is equal to drag, and the aircraft does not lose weight, does not lose altitude or velocity. But if you're talking about an instantaneous turn rate, it is the maximum possible turn rate where, and we do not care about losing altitude or velocity. So the maximum possible turn rate is uh, mainly limited by the structural capability of the aircraft. So in this context, you will remember VN diagram, which we studied in aircraft performance. So this figure it shows a VN diagram. So the vertical component is the vertical axis. We have N, and on the horizontal axis we have the aircraft velocity. So so this means that at this and suppose 200, if you are considering 200 miles per hour, so the unit is miles per hour. So if you're considering 200 miles per hour, then what is the maximum possible load factor the aircraft can turn at? So this is the this graph shows this. Okay, Now there comes a, so in this Venn diagram you will see that the curve is almost like a parabola. Okay, so above this parabola we have a stall area. So it means that the angle of attack to, like if at 200 miles per hour, if we want to turn at load factor 4, then the angle of attack will be so much that it will stall the wings. So we cannot turn at that rate, load factor of 4. Okay, so and you will also see that the in the positive side we can put higher, like we can put higher positive load factors, but not as uh, negative. Like on the negative side we can put the magnitude is lesser. Okay, that is one thing. And the other thing is that you will see that above a load factor, so in this case approximately 7 point load factor of 7. So in this case after approximately n equal to 7, if we cause a turn, then it might cause structural damage. Okay, so above load factor 7 it might cause structural damage. Also there is a upper limit of the velocity, and beyond this velocity the aircraft cannot fly. There might be structural damage, or the engine may not be powerful enough to take the aircraft to that speed. So this is the VN diagram. So this space in between, this is the safe zone where you can fly the aircraft. So over here, if you want to take the tightest possible turn, okay, if you want to fly at the sharpest rate, okay, then we have to fly at the maximum possible load factor. Okay, so this is that point. Okay, the point marked by B. So here we have the highest possible load factor, okay, which is still safe to fly at. So, and the velocity corresponding to this is known as the corner velocity. So here in this figure, V star is the corner velocity. Okay, so then here are some related formulas. So what you can do is, if you know the load factor and the velocity, you can find the turn rate. Okay, but let us say that you are given the turn rate as some kind of specification. Okay, so if you are given as a mission specification the turn rate, then you can find the corresponding load factor using this formula. Okay, now whatever you do, once you have the load factor, you can find the wing loading using this formula. This is quite simple. Okay, you can derive it from this equation. So here CL max is the maximum possible CL during flight. Okay, this does not consider the flaps usually. Okay, so maximum possible CL during flight. Now how do we derive this formula? You can expand this equation. So you can write QS CL max equal to n wave, and from here you can find W by S equal to Q CL max by uh, n. Okay, so that is a instantaneous turn rate. Now I am going to discuss about sustained turn rate. Okay, so for sustained turn rate we have this equation: lift is equal to NW and thrust is equal to drag. So in this case we get a more uh, we get some more restrictions. Okay, and the equations also become complicated. So what you can do is the we know that thrust is equal to drag, and drag we can write as QS CD naught plus KCL square. Okay, and from here also we can write that lift is equal to NW, which is equal to QSCL. Hmm. So from here we can find CL and then we can substitute that CL in this thrust equation. So from here we can find CL as NW by QS. So when you substitute the CL here, you get thrust is equal to QS CD naught plus K M square W square Q square S square. Okay, and when you expand it, you get this equation. Okay, and here you also know that K equal to 1 by pi aspect ratio into Oswald efficiency factor. Okay, now what you do is you divide by weight. Okay, so when you divide the equation by weight, you get this equation. Okay, here you can see that thrust by weight and weight by S, wing area. These terms come into the picture. Okay, now this wing loading, it appears as a quadratic term. So when you then you can solve it. Okay, you have to use it will become a quadratic equation in the form of wing loading, and then you can use the quadratic formula to get an equation like this. Okay, so hmm, to get an expression for the wing loading, so you can use the quadratic formula to get an expression for the wing loading, and you can see that it mainly depends on the uh, thrust to weight ratio. Okay, now some observation you can find from here that uh, the wing loading, it has to be a real value, right? It cannot be an imaginary value. So it means that the term under the square root, it has to be positive. So it means that T by W square minus 4n square CD naught CD naught by pi aspect ratio E. Okay, this term has to be greater than 0. So when you solve it, you will get this expression. Okay, so it means that if we want to, suppose we want to fly at load factor of 2, we want to take sustained turns at load factor 2, then we require at least this much thrust to weight ratio. Okay, so we need at least this much amount of engine power. Okay, now moving on, now let us discuss the wing loading for climb and glide. Wing loading for climbing flight and gliding flight. So for climbing, we can draw the free body diagram like this. Okay, and if you split the forces along this thrust drag axis, you will find that thrust minus drag minus lift sine gamma equal to 0, and thrust minus drag minus lift sine gamma equal to 0. So you can now rearrange it. Okay, so Wait a minute. So okay, now over here we'll make an assumption. Okay, so now what is lift by weight? Okay, here we'll make an assumption that lift is approximately equal to the weight. This is valid when the climb angle is close to zero. Okay, so when we have a small climb angle, then the lift is approximately equal to the weight. Okay, climb angle is not zero, but it is not very large. So then these terms will cancel and we will get sine gamma, which is equal to g. This is thrust minus drag by weight. So this is the quantity over here, which is the in the book they call it the climb gradient, and this is equal to sine gamma. Okay, you can also write it as the vertical velocity by the cruise velocity. Okay, now then you rearrange this equation to get this drag by weight equal to thrust by weight minus g, and drag you can again expand in this form. Like as we saw in the previous slide, you can expand it in this form, CD naught plus KCL square. Okay, and again, so you can write drag is QS CD naught plus KCL square, and then you can write lift is equal to uh, weight, it is equal to QS CL, QSCL. So from here, then su- you can find out CL and then you can substitute the CL in this equation. Okay, when you do all of that, you will get this equation. Drag by weight is this. So again, we will find here that the wing loading terms come into the picture and they form a quadratic equation. Okay, the wing loading forms the quadratic equation. Then you can solve the quadratic equation using quadratic formula to get this kind of a solution. Okay, so over here you will find that uh, thrust loading minus the climb gradient. Okay, these terms they play a important role in this equation. Okay, again again you will note that the term inside the square root it has to be a real number, right? It cannot be an imaginary number. So the term inside the square root must be positive. So when you do that, you will get this kind of a solution. Okay, it shows that the thrust loading has to be at least equal to the climb gradient. Okay, it has to be at least equal to the climb gradient. Now we can also use this equation for other purposes also, like we can use it to find the wing loading for gliding, and we can also use it to find the wing loading at the maximum ceiling or the even at the service ceiling. So to find the wing loading at gliding, what we do is we substitute T by W equal to 0, and we set G equal to some negative number. G equal to negative. It has to be a negative quantity because you know that when you're gliding, the gamma is negative, right? Gamma is negative. So when you do that, you can also find the wing loading for gliding. Uh, and to find the service ceiling, we you put maximum TW, T by W max, and you put G equal to 0. That will give you the wing loading at the service ceiling of the aircraft. No, sorry, not the service ceiling, the absolute ceiling. Okay, now moving on. Now we'll discuss the wing loading for cruise flight. So for cruise flight, you know that there are four combinations. You know that there are four combinations. You can have jet and prop, and you can have maximum range or maximum endurance. So you know that for maximum range with a propeller aircraft, your CL has to be CD naught by K. So in this table, I'm going to write the CL. Okay. So CL will be CD naught by K. For maximum jet range, it has to be CD naught by 3K. For jet maximum loiter, it will be CD naught by K. And for propeller and maximum endurance, it will be uh, 3 CD naught by K. Okay, so this is the table. So you can use these equations to easily find the wing loading. So like ignore this section. This is for the turn rates. So ignore this section. So what you do is you write now in cruise condition. In cruise condition, you also know the equations. Okay, like the simple equations, which is lift equal to weight and thrust equal to drag. So what you can do is you can write weight equal to lift equal to Q S C L, and then CL you can substitute from here. For example, suppose I want maximum propeller range, so I will write weight equal to QS. Maximum propeller range is this, so I'll write CD naught by K. Okay, now K is equal to 1 by pi aspect ratio E. So when I substitute this here, I get weight equal to QS CD naught pi aspect ratio E. Okay, and this S over here, I can bring it in the denominator and get the wing loading. Okay, so similarly for the other three cases of cruising flight, which are maximum jet endurance, maximum propeller endurance, and maximum jet range, you can find the corresponding expressions by simply following this process. Now moving on, now we'll discuss the thrust loading and the wing loading for takeoff. Okay, so this formula and this figure I have taken from John Anderson's book Introduction to Flight. Introduction to Flight. So for this, first to find the takeoff thrust loading and wing loading, first we have to find the takeoff velocity. Okay, and generally the takeoff velocity is equal to 1.2 times the stall velocity. Okay, so now then we have to find the stall velocity, and as you know that the stall velocity is equal to 2W by S by rho CL max. Okay, so when you substitute it here, you get this formula. V takeoff is equal to 1.2 times V stall, which is this. Okay, so now that we have the takeoff velocity, now what we'll do is we'll draw the free body diagram of the aircraft, and we'll draw all the forces acting on it, and then we'll find the average acceleration. Okay, then you remember this formula from uh, like high school physics, which is that V square minus U square equal to 2AS. Okay, where v is the final velocity, u is the initial velocity, a is the acceleration, and s is the distance. Okay, so here the initial velocity is 0. Okay, so then you can find that the s, which is in this case the s is the takeoff distance. This is takeoff velocity by 2a. Okay, so here so this is the takeoff distance, v is the takeoff velocity, and a is the average acceleration. Okay, so once we find these quantities, we can find the takeoff length. So consider this free body diagram of the aircraft I've shown. So the forces acting on it are the thrust. Okay, the thrust which is pushing it forward, and then you have the lift and the weight, and you have the uh, friction force and also the drag. So you can write that the net net force acting on the aircraft is the thrust minus the drag minus the friction. Okay, so the friction force you can further expand it as weight minus lift. I mean the friction coefficient into the weight minus lift. So thrust minus drag minus mu r into w minus l, and this is equal to the mass of the aircraft into the acceleration. Okay, now as you can see that the net force on the aircraft and hence the net acceleration is going to vary during the takeoff roll. Okay, as the aircraft is accelerating, the drag parameter, the everything actually, the thrust, drag, and the lift, all are going to change during the takeoff roll. So this equation is not strictly valid. Okay, but it is good enough for a first estimate. Okay, like we have to start somewhere, right? So it is good enough for a first estimate. So for a first estimate, we'll assume dl is constant. Thrust, drag, and lift is constant. Now it has been found that if you consider the lift and the drag at zero point 0.7 takeoff velocity, then it is good enough. So consider lift and drag at 0.7 of the takeoff velocity. Okay, so once you do that, you can find out the average acceleration. So this is here a, so this is the average acceleration, and then you can substitute into this formula to get the takeoff distance. Okay, so this is the takeoff distance. Okay, just this thing has to be substituted here. Okay, now you can further substitute this vlo this formula you can substitute over here to get this formula. So okay, this formula, you can make further simplifications on this. Okay, you can assume that this portion, it is less than 10%, okay, of the thrust. Okay, so this contribution is less than 10% of the thrust, so you can also ignore this part. Okay, to get this simple formula. Okay, SLO equal to 1.44 weight square by g rho s cl max t. Okay, so this is a simple formula to calculate the takeoff distance, and here it, I mean that it is good enough for a first guess. Now after the uh, first round of aircraft design has been completed, you have to further refine this guess. Okay, so you have to make changes and you have to refine this guess. But from here you can see that the takeoff distance is proportional to the weight square. It is inversely proportional to the density. It is inversely proportional to the wing area, and inversely proportional to the wing area and CL max and the thrust. Okay. Also in some places you will see that this equation is written in terms of wing loading and thrust loading like this. So you can write W by S G rho. You can also write it like this. Okay. You will find here that the terms wing loading and thrust loading have come here into the picture. Okay. Acha, now one important thing. So, in this takeoff distance calculation, you will find that G and the 1.44. Okay. So these terms are more or less constant. Okay. You can also, these terms are more or less constant. The other terms are variable. So these things you can collect it and call it as a takeoff parameter. So takeoff parameter is defined as weight by S sigma CL max T by W. Okay, and here sigma is rho by rho naught. Rho naught means rho means the place from where you want to take off. Okay, and rho naught is the air density at mean sea level. Okay, so when you do all the substitutions, you will find that the rest of the things are constants, and mainly the takeoff distance depends on these terms. Okay, so this is a statistical chart which I've taken from Raymer's book. So the x-axis is the takeoff parameter, and the takeoff parameter is defined like this: W by S into by sigma CL max T by W, and on the y-axis we have the takeoff distance. Okay, so this is some statistical relationship. Okay, so as a first guess, you can, if you know the takeoff distance. Okay, usually the takeoff distance is specified as a in the mission specifications. Okay, so let us say that you know the takeoff distance, then what you can do is you can find out the takeoff parameter on the using this chart. So this is good for a first approximation. So when you know the takeoff parameter, then you can find the wing loading using this formula. Okay. Conversely, if you know the wing loading, you can find the thrust loading using this formula also. Then moving on, now we'll discuss about high lift devices. So what you can see from the previous expression, what you can see from the previous expression is that the takeoff distance is inversely proportional to the CL max, which means that if we increase CL max, we can reduce the takeoff distance. And similarly, if you look at the takeoff velocity or the stall velocity, they are also inversely proportional to the CL max, which again means that if you increase the CL max, you can simply write it. If you increase the CL max, then the takeoff velocity decreases and the takeoff distance also decreases. Now both of these things are desired because if the takeoff distance is lesser, you can take off from a shorter runway. Okay, you don't require a very long runway then. Okay, and also if the takeoff velocity is lesser, it means that you can get into the air quicker. Okay, and there is more margin for safety. Okay, you can fly at a lower velocity also. So hence it is imperative to increase the CL max. But the problem is that when you increase CL max, so when you increase CL max, the drag also increases. Okay, but this is not desirable. Okay, because it consumes more energy and more fuel. Okay, so if drag is more, then more energy is consumed. And if you look at a aircraft's mission profile, okay, so the takeoff and the landing, they comprise of they only comprise a short duration of the flight, right? If you look at a long distance, like long distance commercial transport aircraft, it might spend it might spend 7 8 hours in the air. So out of the 7 hours, half half an hour might be spent on takeoff and climbing, and half an hour might be spent on the approach and landing. Okay, and the rest of the 6 hours will be spent in cruise. So it is better to optimize the aircraft for the cruising section rather than the takeoff and landing phase. So instead, another mechanism is that we kind of make the wings flexible. Okay, what we can do is we can make the wings flexible such that during takeoff and landing, the wings produce a lot of lift at the cost of more drag, but during the cruise section, the wings do not produce so much lift, okay, and hence the drag is reduced. So the way this is achieved is using high lift devices which are fitted to the wing. Okay, so these are mainly of two types: flaps and slats. So flaps are usually some moving part of the wing which are attached at the and trailing edge, and they can bend downwards to increase the camber of the wing. Okay, so if you look at this plain flap, so here there is a joint which can move the flap down like this. Okay, so this increases the camber of the wing, and so the wing produces more lift and also more drag. During takeoff and landing, this flap will be extended down to have a higher CLmax, but during cruise, this flap will be retracted such that the drag is not that high. Then you also have something called a slotted flap. So in case of a slotted flap, there is a gap between the wing and the flap. So here actually, even though a gap is shown, but theoretically there is no gap. But in case of a slotted flap, there is a gap here and the airflow can flow through this gap. And this has shown to increase the CLmax. Okay, like this slotting mechanism has shown to increase the CLmax. So a slotted flap will have a higher CLmax. Then you also have a split flap. So a split flap, in the split flap, one part of the wing will split and go down like this. Okay, there is also something called zap flap. So here it is similar to a split flap, but it also moves outwards. So it comes down and it also moves back. So this increases the wing area also. So here the wing area also increases. So since the wing area is more, it produces more lift. You also have the Fowler flap. The Fowler flap is like a plain flap or a slotted flap, except that it moves back. So when it moves back, the wing area increases. So all these things they contribute to a higher lift during landing. Then you also have double slotted flap. So you can see that one slot it increases the CL max. What you can do is you can put more slots. Okay, so you can put more slots. So this will further increase the lift. Okay. You also have triple slotted flaps, which again increase the lift. Another thing you can do is you can put slat. Slat is slat is like this flap only, but it is positioned at the leading edge of the wing. It might also have a slot like this from the air from which the air can pass. So again, this mechanism also increases the CL. And if you want some numbers, then the CL can reach on the range of 3 also. With these flaps, with these kinds of flaps, the CL can reach in the range of 3, whereas with plain flaps, the plain wing or plain flaps, the CL approximately is at the range of 1 CL max. I'm talking about CL max. So you can see that this is a almost 3 times increase in the uh, lifting capabilities of the wing. Okay, so this will reduce the both the stall velocity, the landing takeoff velocity, and also the takeoff distance. Okay, so this was some examples of high lift devices. Now we'll discuss the wing loading for approach and landing. So for approach and landing, we'll use a statistical approach. Okay, so from a statistical approach, it has been found that Approximately the landing distance, it is related to the approach velocity using this formula. So here the VA is the approach velocity. So the landing distance is approximately equal to 35% of approach velocity square. So this is a statistical relationship. Now also the approach velocity is equal to 1.3 times v stall velocity. Okay, this is also found through observations. So and you know that the stall velocity can be found using this formula. So now you can substitute everything and you can calculate the W by S for landing. Okay, if you know all these things, okay, usually the S, okay, so usually the S land will be given, okay, in terms of a specification. So when you know S land, you can find out the approach velocity like this, okay, and then from approach velocity you can find out stall velocity, and then from stall velocity you can find out wing loading. So given S land in the mission specifications, find approach velocity, and then from here find stall velocity, and then find W by S. So that is what is given in this formula. So you basically take this thing and you invert it, okay, you will get this. Okay, here you can see the VA by 1.3 is the stall velocity. Okay, so now I'll discuss some examples. I mean not examples, some exercises. So this is the first question. So obviously over here, if the thrust to weight ratio increases, then the takeoff distance will decrease. So when, as we saw in the formula, that the takeoff distance is approximately equal to 1.44 weight square by rho s g cl thrust. So if the thrust to weight ratio, you can see that the thrust is at the denominator. So if the thrust to weight ratio increases, then the takeoff distance will decrease. Now moving on. So this is the second question. So here the answer is greater than 1. So this means that so if you consider an aircraft during takeoff, so it will accelerate from here to here, and then it will pitch up like this until it clears a 50-foot obstacle. So when it clears 50-foot altitude, then the aircraft is said to have taken off. Okay, so this whole phase is called takeoff. So this question is talking about this phase. So when the aircraft is climbing a little bit, so transition phase. So over here you can see that the aircraft is actually like performing a maneuver. Okay, because it is pitching up like this. So and we know that during a maneuver the load factor is always greater than 1. So that is why the load factor during this phase is also going to be more than 1. Okay, so this is the third question. Okay, so this question is actually about landing. Okay, this is not about takeoff, this is about landing, but the equations are similar. So when you consider an aircraft uh, during the landing phase, okay, so there also you have drag, and you have frictional forces, you have lift, you have weight, okay, and you may or may not have thrust. Okay, so you might have reverse thrust. Okay, so but this reverse thrust may not be there also. Okay, if the aircraft does not have thrust reversers, then this may not be there. So equations are almost the equations are actually exactly similar to the takeoff equations. Okay, so if you remember the takeoff equation, it was that SLO equal to 1.44 W square by rho g s CL max into thrust by thrust. Okay, so you see that the thrust is in the denominator. Okay, so the takeoff distance will be proportional to 1 by T ref. Here you can also say that it is proportional to 2 by T ref. I think there is a mistake in the question then, but the more correct answer is this 1 by T ref. Then I'm moving on. So this is the question, fourth question. So I think you can easily solve this. This is the same as the previous question, just this is for takeoff instead of landing. So here also I think the correct answer will be this. Okay, although this answer is also correct, but the more correct answer is the first one, 1 by T. And then you have the fifth question. So here also you will, so this question is also talking about landing. So again, if you write the equation, so you can see that the CL term, it comes in the denominator. Okay, so if CL increases, then the landing ground roll distance, it will decrease. So when the flaps are deflected, then the CL increases, right? So therefore, when the CL will increase, then it will decrease the ground roll distance. So therefore, here the ground roll distance will decrease. Okay, so that is it for today's session. So thank you for joining.